Something is out there that should not exist. A structure 10 billion light-years across, inside a universe only 13.8 billion years old, forming faster than gravity allows, and stretching farther than every equation permits. Astronomers found it in their data, and their first instinct was to look for the mistake. There was no mistake. We are going inside the largest known structure in existence. We will explore the invisible dark matter scaffolding holding the cosmos together, visit a void so empty it would have hidden other galaxies from us entirely, and follow the chain of impossible anomalies, now cracking the foundation of everything cosmology thought it understood. If you enjoy what we uncover, please like and subscribe. It keeps us going. Prepare yourselves. We begin. The instruments had been working without incident for years, cataloguing the universe's most violent events one by one. Gamma-ray bursts arrive at detectors the way lightning strikes appear on a weather log, sporadic, brief, and each one an explosion so powerful it briefly outshines every single star in an entire galaxy combined. The team of Hungarian astronomers running the mapping project had not set out to find anything extraordinary. They were doing the patient, careful work of science, collecting data, building a picture, adding entry after entry to a growing catalogue of these cataclysmic events. Year after year, the catalogue grew, and year after year, the picture it assembled looked more or less the way the models said it should look. Then it stopped looking right. The bursts in a particular region of sky were clustering in a way the statistical models could not explain. Gamma-ray bursts should be scattered somewhat randomly across the sky, tracing the broad distribution of galaxies throughout the cosmos. Occasional clustering is expected, but in this region, toward the constellations Hercules and Corona Borealis, the bursts were accumulating with a frequency that the models predicted should appear only once in several million random samples. The team ran their significance tests. They rechecked the data for instrumental errors. They asked whether some quirk of detection sensitivity was artificially concentrating the sample in this direction. Every check came back clean. The clustering was real. What the clustering was tracing was staggering, a structure spanning roughly 10 billion light-years from end to end. The team named it the Hercules Corona Borealis Great Wall. When the announcement came, the cosmological community's first reaction was calibrated skepticism, the appropriate professional response when a result challenges something as fundamental as this one did. The second reaction, once the numbers held up under independent analysis, was something harder to categorize, something more like alarm, because the problem was not simply the size. The problem was what the size implied about a universe that has only existed for 13.8 billion years. A structure 10 billion light-years across, formed within a 13.8 billion-year-old universe, represents a violation of the deepest physical principle in cosmology. The universe did something it should not have been able to do, and the more carefully you look at the evidence, the harder it becomes to find the mistake. The maximum scale for a coherent, large-scale structure, given the time available since the Big Bang and the known physics of how gravity builds structure, is approximately 1 billion to 1.2 billion light-years. The Hercules Corona Borealis Great Wall is 10 billion. It is somewhere between 8 and 10 times larger than the known physics permits. Structure forms through gravity's patient amplification of tiny initial density differences over billions of years, and that process is constrained by the age of the universe, the speed of light, and the strength of gravity itself. None of these constraints leave room for a 10 billion light-year structure. Something is wrong with the calculation, or something is wrong with the model, or both. The search for the answer to this question will take us through the deepest mysteries in modern cosmology, from the invisible skeleton of the universe to the force tearing it apart, and ultimately to the possibility that our universe has been touched by something that exists outside it entirely. Gamma-ray bursts are among the most energetic events in the observable universe. They occur when the most massive stars reach the absolute end of their lives and collapse into black holes in a matter of seconds. They also occur when two neutron stars, the dense remnants of smaller stellar explosions, spiral toward each other under gravity and finally collide and merge. In either case, the resulting explosion releases more energy in a few seconds than our star will emit across its entire 10 billion year lifetime. The burst of gamma radiation that follows is powerful enough to be detected from virtually anywhere in the observable universe, cutting through billions of light years of intervening space with a clarity that makes these events extraordinary tools for mapping the large-scale distribution of matter. Satellites like the Fermi Gamma Ray Space Telescope and the Swift Observatory catch roughly one detectable gamma-ray burst per day. Each one is a signal fire lit by a dying or colliding stellar remnant, marking the position of its host galaxy with a precision that visible light surveys struggle to match at great distances. The host galaxy may be too faint to detect directly at its distance of billions of light-years, but the gamma-ray burst announces its position with unmistakable clarity. Map enough of these signal fires across enough of the sky, and the underlying distribution of galaxies becomes readable in their pattern. Galaxies gather in clusters. Clusters string along filaments. Filaments interconnect into the walls and sheets of large-scale structure. The pattern of gamma-ray bursts reflects the pattern of the galaxies that contain them. The clustering in the Hercules corona borealis direction spans roughly a third of the visible sky. At distances between about 5 billion and 11 billion light-years, bursts accumulate with a frequency that cannot be explained by chance alone. The statistical significance runs to approximately 5 sigma, which is the standard threshold for a discovery claim in physics. The probability of this excess arising from random fluctuation is less than 1 in several million. Independent analyses using different statistical methods, different subsets of the burst catalog, and different corrections for known biases all confirm the excess. Whatever is causing the clustering is real. The important caveat is that the Hercules corona borealis Great Wall is a statistical detection rather than a direct imaging. We cannot see it the way we see galaxy clusters or filaments in nearby surveys. The distances involved are too vast, the light from individual galaxies within it too faint, the resolution required too fine. We know it is there the way a doctor knows something is wrong from a blood test, without seeing the underlying tissue directly. The evidence is indirect but solid, and the interpretation, a structure of 10 billion light-years, has survived years of scrutiny without being explained away. The signal fires are piled up because the galaxies holding them are piled up, and those galaxies are organized into something that, by every principle cosmology depends on, should not be possible. What that principle is, and why it matters so deeply, is the next question. The cosmological principle is the foundational assumption of all modern cosmology. It states that the universe, on large enough scales, is the same in every direction and from every location. Homogeneous, meaning equally dense everywhere, when averaged over a large enough volume, and isotropic, meaning looking the same regardless of which direction you face. This is not a modest or incidental assumption. It is embedded in the mathematical bedrock of the field. The Friedmann equations, which describe how the universe expands and which underpin every calculation of the universe's history and fate, are derived assuming the cosmological principle holds. The standard cosmological model, lambda CDM, assumes it at every level. Every precision test of cosmology performed in the last 30 years has been interpreted within a framework that takes the principle as given. The principle is not arbitrary. It emerges naturally from the physics of the Big Bang. If the universe began in a state of near-perfect uniformity, which the cosmic microwave background confirms it did, and if it has been expanding and evolving according to known laws, then, on scales large enough to average out the local variations caused by structure formation, it should indeed look the same everywhere. No region should be distinctly denser or emptier than another at the largest scales. No direction should be distinguishable from another. The universe should, at sufficient zoom, be featureless and smooth. The scale at which this smoothness is supposed to kick in is roughly 1 billion light-years. Below this scale, the cosmic web and its structures are expected and accounted for. Above this scale, the standard model says the universe should look smooth in every direction. Surveys should show the same average density regardless of which patch of sky they sample. And for most surveys at most scales, this is approximately true. The large-scale distribution of galaxies is broadly consistent with homogeneity. The standard model works most of the time. But above about 1 billion light-years, something starts going wrong. The Sloan Great Wall, at 1.37 billion light-years, pushed against the limit. The Giant Arc, at 3.3 billion light-years, broke through it. The Big Ring, at nearly 4 billion light-years in circumference, reinforced the breach. And the Hercules Corona Borealis Great Wall, at 10 billion light-years, is not pushing against any limit. It is standing 8 times beyond it, a structure that cannot exist in a smooth, homogeneous universe. In a universe that demonstrably does not look smooth at this scale. The cosmological principle, the bedrock of every cosmological calculation performed in the modern era, may be wrong. Or it may be a good approximation that breaks down at scales we are only now mapping. Either way, the implications run through every equation in cosmology. If the principle fails, the model built on it needs to be revised at its foundation. The Lambda CDM model is one of the most successful theoretical frameworks ever constructed. Lambda stands for the cosmological constant, Einstein's symbol for dark energy. CDM stands for cold, dark matter. Together, these two invisible components, combined with ordinary matter and the known physics of gravity and particle interactions, produce a model that describes the universe's history and large-scale structure with extraordinary accuracy. The model explains the temperature variations in the cosmic microwave background to better than 1% precision. It accounts for the formation of galaxies, the clustering of matter on scales from individual galaxies to superclusters, and the abundance of light elements produced in the first few minutes after the Big Bang. It is a genuine triumph of scientific model building, refined over decades by thousands of researchers using the most precise instruments ever built. When you run a computer simulation of the universe using Lambda CDM as your rulebook, the simulated cosmos matches the one we observe in an impressive range of features. The simulated sky shows a cosmic web of filaments, walls, and voids that matches the structure seen in galaxy surveys. The simulated galaxies form with masses and shapes consistent with what telescopes observe. The simulated distribution of galaxy clusters matches the statistics of real catalogs. At scales below about 1 billion light-years, the model and reality agree well enough to call it a success. This is why it has remained the standard framework for so long, and why challenges to it are taken seriously only when they accumulate evidence too substantial to dismiss. The model does have known tensions. The Hubble constant, the measurement of how fast the universe is expanding today, gives different values depending on how you measure it, and those different values disagree at a level that cannot be attributed to measurement error. The distribution of mass within galaxies does not always match what cold, dark matter simulations predict at small scales. Some clusters of galaxies are larger or more massive than expected. Each of these tensions has been studied extensively, and proposed solutions exist, but none are confirmed. The model absorbs these tensions as open problems, rather than fatal flaws. The impossible large-scale structures are different in character. They do not suggest a tension within the model. They suggest the model is missing something at a fundamental level. A structure 8 to 10 times larger than the maximum allowed by the model is not a tension, it is a contradiction. Either the structure is not what we think it is, or the model is not what we think it is. The cosmological community is divided on which horn of this dilemma to take, and the debate is productive and ongoing. But the existence of the debate itself tells you something important. The Standard Model, for all its extraordinary success, is showing cracks at its upper boundary, and those cracks are deepening with every new survey that maps the universe at larger and larger scales. The next level of our story is the structure that the model was built on, the architecture beneath the anomalies, the web that connects everything. Pull back far enough from Earth, and the universe reveals its true face. Not a random scattering of stars and galaxies, not a smooth, uniform medium, but a vast, three-dimensional web of filaments and voids that spans the entire observable cosmos. This is the cosmic web, the large-scale architecture of the universe, and it is one of the most breathtaking structures in the history of science. Long, thin threads, each one a river of dark matter and hot gas and galaxies stretching for hundreds of millions of light-years, extend across the cosmos and connect at dense nodes where the most massive galaxy clusters sit. Between the threads and nodes are the voids, enormous bubbles of near emptiness that account for most of the universe's volume. The web looks almost organic when rendered from survey data, almost alive, a structure without a center, without clear boundaries, repeating its branching pattern at every scale you choose to examine it. The web was predicted before it was observed. In the 1980s, the first computer simulations of cosmic structure formation produced it spontaneously. Researchers running those early simulations watched, on their primitive hardware, as the smooth initial conditions of the Big Bang evolved under gravity into a web of filaments and voids that matched, at least in its general character, the structures they were beginning to see in galaxy surveys. When larger and more detailed surveys confirmed the web's existence in the 1990s and 2000s, it was celebrated as one of the great confirmations of the Standard Model. Theory and observation agreed. The web was real. The simulations had gotten it right. The cosmic web forms from the smallest possible seeds. In the universe's earliest moments, quantum fluctuations, the random statistical variations that quantum mechanics requires to exist at every scale, in every field, were present in the density of the early cosmos. Ordinarily, these fluctuations would be entirely inconsequential at scales larger than atoms. But during inflation, the period of explosive exponential expansion in the universe's first tiny fraction of a second, these quantum fluctuations were stretched from subatomic scales to cosmic ones. Those stretched fluctuations became tiny variations in the density of matter and energy across space, and those variations became the seeds of all structure. Regions fractionally denser than average attracted surrounding matter through gravity. As more arrived, the gravitational pull deepened, attracting more still, in a feedback loop that ran for hundreds of millions, then billions of years, building filaments from whispers of overdensity. The terrifying beauty of this is the connection it implies between the largest and smallest scales. The cosmic web, stretching for billions of light years, is a direct amplification of quantum noise. The filaments, whose intersections hold clusters of thousands of galaxies, grew from fluctuations smaller than a proton. The largest structure in the universe, the Hercules Corona Borealis Great Wall, is in some sense a very large quantum fluctuation, inflated and then shaped by gravity across cosmic time. The quantum world and the cosmic world are not separate domains. They are the same story told at different scales, and the web is the most visible expression of their connection. The cosmic web appears, in galactic maps, to be made of light. Filaments glow with the stars of hundreds of billions of galaxies. Nodes blaze with the concentrated brightness of enormous galaxy clusters. But all that light, all those hundreds of billions of stars, and the gas and dust and radiation associated with them, represents only about 5% of the universe's total mass energy content. The remaining 95% is invisible. Roughly 27% is dark matter, something that interacts gravitationally but produces no electromagnetic radiation of any kind. Roughly 68% is dark energy, a mysterious force driving the accelerating expansion of the universe. The cosmic web is not made of the glowing things we see. It is made mostly of the invisible things we cannot. Dark matter is the true skeleton of the web. Long before the first galaxy formed, dark matter was already clustering and organizing itself under gravity, building the invisible scaffolding around which visible matter would eventually gather. The dark matter filaments formed first, pulling hydrogen and helium gas into their gravitational embrace, seeding the formation of the first stars and galaxies billions of years later. What you see when you look at a map of the cosmic web is not the structure itself. It is the lit border of an invisible architecture, the glowing edge of something far larger and more massive that we can only infer from its effects. Those effects are unambiguous. Galaxies rotate at speeds that require far more mass than their visible stars can provide. If a galaxy contained only the matter we can see, its outer regions would fly apart, unable to maintain their orbits against the centrifugal force. Dark matter halos, extending far beyond the visible disk of each galaxy, provide the additional gravitational mass that holds them together. Galaxy clusters bend the light from background objects in a pattern called gravitational lensing that requires mass far exceeding their visible content. The growth of large-scale structure from the smooth early universe to the complex web we observe today requires a component of matter that started clustering earlier and more effectively than ordinary matter, providing the gravitational wells that visible matter fell into. Every test of the dark matter hypothesis in every domain confirms its necessity. The universe without dark matter does not resemble the one we inhabit, and yet no experiment has directly detected a dark matter particle. The history of dark matter detection is a long record of null results from increasingly sensitive experiments. The Large Underground Xenon detector ran for years with no confirmed dark matter signal. Its successor, the Lux-Zeppelin experiment, achieved extraordinary sensitivity and found nothing. The Panda X experiment in China found nothing. Every candidate particle that theoretical extensions of the standard model of particle physics predicted might be dark matter, the WIMPs, the axions, the sterile neutrinos, has been searched for in experiments that should have detected them if they exist within the predicted property ranges. The searches have come up empty. The backbone of the cosmic web is made of something we have never found, something that defeats every detector we build, something whose existence is certain and whose nature is entirely unknown. The scaffolding holds the universe together, and we cannot see it, touch it, or identify it. The cosmic web is shaped not only by what it has, but by what it lacks. For every dense filament, there is a region where matter has been evacuated, pulled outward over billions of years toward the denser walls and clusters surrounding it. These are the voids, and at their largest they are called supervoids, regions of space so underdense that they represent the nearest thing to true emptiness that the universe achieves at scales above a single galaxy. Voids are not static. They grow as the universe ages, expanding as dark energy drives the overall expansion and as matter continues flowing outward along the pressure gradients, created by the denser structures at their boundaries. The Beta supervoid is the most intensively studied supervoid in the observable universe. It spans roughly 330 million light-years and contains only about 60 known galaxies, where the cosmic average density would predict several thousand. The interior is not completely empty. Space continues through it without interruption. A handful of galaxy groups and isolated galaxies exist within it, distributed sparsely around its edges and center, but the density reduction is more than 90%, making it the emptiest large-scale region mapped so far. To understand what this means experientially, consider living in the center of the Bootes void. The nearest galaxy clusters lie hundreds of millions of light-years away, at the boundaries of the void where the cosmic web resumes. With the telescopes available to humanity for most of recorded history, those clusters would be invisible. With the naked eye, the sky would show only the stars and nebulae of our own galaxy. the same view that led early astronomers to believe the Milky Way was the entirety of the universe. The discovery that other galaxies existed at all, which came with the observations of Edwin Hubble in the 1920s using the best telescopes of that era, would have been delayed by decades or longer. The idea that the universe contained billions of galaxies spread across billions of light years would have remained beyond reach. The void would have hidden the scale of the cosmos entirely, preserving an illusion of a single galaxy universe until instrumentation sophisticated enough to bridge the vast distance to the void's boundaries was developed. For decades, the Boötes void sat at the edge of what simulations of cosmic structure formation could reproduce. It was larger and emptier than the standard model comfortably predicted, yet not so dramatically anomalous as to demand immediate revision. It was filed as a curiosity, an outlier at the upper end of expected void sizes. Then other discoveries arrived and made it look almost ordinary by comparison. The Boötes void is not the strangest emptiness in the observable universe. The strangest emptiness is not a void at all, but a shadow in the oldest light, a cold patch on the sky whose explanation may require looking beyond the boundaries of the universe itself. The cosmic microwave background is the oldest light in existence. Released roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons and form neutral hydrogen, this glow has been traveling through space ever since. As the universe expanded, the radiation cooled from several thousand degrees to just 2.7 degrees above absolute zero. Today, it fills all of space as a bath of microwave radiation, arriving from every direction with a uniformity that is one of the most precisely tested facts in all of physics. The temperature variations in this background are only about 1 part in 100,000. The pattern of those variations encodes the conditions of the infant universe, 380,000 years after the Big Bang, and matches the predictions of the Standard Model with extraordinary precision. The cosmic microwave background is the Standard Model's strongest evidence and its most precise test. Almost everywhere, the test passes. The observed temperature variations match the predicted pattern at a level of agreement that represents one of the greatest confirmations of any physical model in history. Cosmologists compare the data against theory and find agreement that would satisfy any scientist almost everywhere. In the direction of the constellation Eridanus, there is a region of the background sky that is colder than expected, about 70 microkelvins colder, which is a tiny fraction of a degree. But the statistical significance of the deviation runs to several standard deviations. The cold spot was first detected in 2004 in data from the WMAP satellite. It was confirmed by the Planck satellite, more sensitive and more precise, in subsequent years. Every recalibration, every check for instrumental artifacts, every search for foreground contamination has failed to explain it. The cold spot is not a measurement error. It is a real feature of the cosmic microwave background, and it has a size of roughly 1.8 billion light-years in angular extent. The simplest explanation is a large supervoid along the line of sight. When photons from the background travel through an underdense region, they lose energy through a process called the integrated Sachs-Wolf effect. The gravitational well they cross is growing shallower as they exit, because dark energy is expanding the void while they traverse it, so they emerge with slightly less energy than they entered with and appear colder. A supervoid of sufficient size and depth in the direction of Eridanus could explain the temperature deficit, and surveys do reveal a supervoid in that direction, but the supervoid found is not large enough or deep enough to explain all of the cold spot. The numbers do not close. The supervoid explains part of the anomaly. The rest requires something else. That something else, according to one hypothesis taken seriously by reputable physicists, is a scar left by contact with another universe. In the framework of eternal inflation, our universe is a bubble. The inflationary expansion that preceded and produced our Big Bang did not end uniformly everywhere. In most of the volume of the inflationary medium, inflation continued forever. Our universe nucleated within this endless inflationary background, when a quantum fluctuation allowed a local region to exit inflation and undergo a big bang of local physics. Other such nucleations happened elsewhere, at other times, in other regions of the inflationary background. Each nucleation is a bubble universe. Each bubble expands. Each has its own physical laws, its own particle content, its own constants of nature, potentially completely different from ours. Bubble universes expand within the inflationary background, but they can also collide. When two bubbles are nucleated, sufficiently close together in the inflationary medium, they can grow into contact. When they collide, the collision injects energy anisotropically into the boundary region between them. The collision front sweeps through the interior of one or both bubbles, heating matter and radiation in the affected region. In the surviving bubble, the collision leaves a characteristic imprint on the cosmic microwave background, a roughly circular region of anomalous temperature with a specific temperature gradient at its boundary. The shape of the imprint, the temperature profile, from center to edge, carries information about the collision geometry and the properties of the colliding bubble. The cold spot has characteristics consistent with such an imprint: the circular geometry, the temperature profile, the angular size. These are not unique to the bubble collision hypothesis, and other explanations exist. But the collision hypothesis is consistent with the data in ways that have not been conclusively ruled out. Some researchers have gone further, fitting detailed collision models to the cold spot and finding that the data is not inconsistent with a specific class of bubble collision geometries. The fit is not perfect, and the model is not unique, but it has not been falsified. If the cold spot is what the bubble collision hypothesis says it is, the implications are staggering. In the oldest light in the universe, we have a physical imprint of contact with something outside our cosmos. Another universe, with its own physics, reached the boundary of ours and left a mark. We are not alone in the largest possible sense. Our universe exists within a multiverse of bubble universes, and at least one of those other bubbles has already touched ours. The universe is not everything. It is one instance among many, separated from the others by a physics we cannot enter or observe, but not entirely isolated from them. One of them left its fingerprint on the oldest light we can see. We are only beginning to understand what that means. The cosmic web fills nearly all of space with visible structure and vast emptiness, but it hides something even within the regions of densest structure. For decades, after the standard model of cosmology began making detailed predictions about the universe's matter content, a significant fraction of ordinary matter was simply unaccounted for. The standard model predicted that roughly half of all the ordinary matter in the universe, protons and neutrons forming the hydrogen, helium, and heavier elements of the cosmos, should exist in a diffuse state between galaxies, caught in the filaments of the cosmic web as a very hot, very thin gas. This material was called the warm-hot intergalactic medium. It was predicted to be heated by the compression of falling into filaments to temperatures between 100,000 and 10 million degrees, and to fill the bridges between galaxy clusters with a nearly invisible mist of superheated plasma. Nearly invisible is not completely invisible. At these temperatures, the gas emits X-rays and can interact with light passing through it in specific ways. But the emission is spread across such enormous volumes and is so diffuse that detecting it directly requires extraordinary sensitivity. For decades, the predicted warm-hot intergalactic medium was one of cosmology's embarrassing loose ends. The standard model said it had to be there. The observations could not confirm it. Roughly half of all the ordinary matter that had existed since the Big Bang had apparently gone missing. In 2020, X-ray observations from the XMM Newton satellite finally confirmed direct detection of the warm-hot intergalactic medium in filaments connecting galaxy clusters. The missing baryons were found. They had been there all along, trapped in the filaments of the cosmic web, emitting in wavelengths that previous instruments had insufficient sensitivity to detect. The universe had hidden half of its ordinary matter in plain sight, written in superheated gas. threading through the spaces between galaxies in structures spanning hundreds of millions of light years. The discovery was a triumph for the Standard Model. In one sense, the predicted material was where the theory said it would be. But it also underscored a deeper point about the limits of observation. We had been studying the universe for decades with the most sophisticated instruments available, and half of its ordinary matter had been invisible to us the entire time. If we missed half of ordinary matter for so long, the question becomes unavoidable. What else are we missing? The dark matter we cannot find, the dark energy we cannot explain, the impossible structures that break the models. These anomalies exist in a universe that has already proven capable of hiding half of the stuff we can directly measure. The catalogue of what we do not know is almost certainly larger than the catalogue of what we do. Every great discovery in science begins with an unexpected signal. The data does something the models did not predict. The instruments read a number that does not fit. A pattern appears in a place where no pattern should be. What separates a trivial anomaly from a genuine discovery is whether the unexpected signal persists through scrutiny, survives independent confirmation, and resists every attempt to explain it away within the existing framework. The cosmic microwave background cold spot has survived every test applied to it for 20 years. The Hercules Corona Borealis Great Wall has survived every statistical challenge since its announcement. The large-scale anomalies accumulating in galaxy surveys have survived the construction of each new, more precise instrument. The impossible structures are not going away. They are getting more numerous and better confirmed with each passing year. This accumulation matters. A single anomaly can often be accommodated within a theory through minor adjustments or reinterpretation. Two anomalies pointing in the same direction are harder to dismiss. A pattern of anomalies, each independently confirmed, each pointing toward the same conclusion from a different direction, eventually stops being a collection of exceptions and becomes the new signal. The Hercules Corona Borealis Great Wall, the Giant Arc, the Big Ring, the Cold Spot, the Hubble Tension, the James Webb Space Telescope's two massive early galaxies. These are not separate problems with separate explanations. They are different measurements of the same underlying reality, and that reality appears to be one in which the universe's behavior at the very largest scales does not match what the Standard Model predicts. The question is not whether something is missing from the model. The evidence strongly suggests something is. The question is, what? The answer will require a revision of cosmology at a foundational level, and it may reveal new physics that changes our understanding of the universe's composition, history, or even the laws that govern its evolution. We are at the beginning of that process. The anomalies have been found and confirmed. The model is under pressure. The theorists are working. What comes next? In the ongoing story of the cosmic web and the impossible structures embedded within it, will push the stakes even higher. The supervoid at the direction of the cold spot presents an additional layer of this puzzle. Surveys have confirmed a large underdense region in that direction, at a distance of roughly 3 billion light-years, that is emptier than the typical void. But the detailed temperature profile of the cold spot does not perfectly match the profile expected from a supervoid of the size and depth that surveys reveal. The supervoid can account for some of the temperature deficit, but not all of it. The gap between what the supervoid explains and what the cold spot shows has been the subject of ongoing analysis. Larger supervoids, deeper than the surveys suggest, could close the gap, but the surveys themselves constrain how empty the region can be, without the galaxies they detect becoming inconsistent with the data. The cold spot remains stubbornly larger and deeper than the supervoid can fully account for. This residual anomaly is what keeps the bubble collision hypothesis alive in serious scientific discussion. It is not the only hypothesis. Some researchers have proposed that the cold spot is a statistical anomaly that becomes less surprising when the right multiple testing corrections are applied. Since the sky contains many regions, and picking the most anomalous one after the fact inflates its apparent significance. Others have proposed textures, topological defects from the very early universe, as the source. Each hypothesis has its advocates and its critics. None has been conclusively confirmed or ruled out. The cold spot remains one of the most carefully studied and least explained features of the cosmic microwave background. A persistent question mark written in the oldest light we can observe, pointing at a region of the sky where something we do not fully understand left a mark on the fabric of the universe. In 2003, astronomers completing the Sloan Digital Sky Survey announced the first truly detailed, three-dimensional map of the nearby universe. More than 200,000 galaxies mapped out to a distance of roughly 2 billion light-years. When researchers analyzed the large-scale structure this map revealed, they found a wall of galaxies that exceeded anything previously mapped. The Sloan Great Wall stretches about 1.37 billion light-years, making it, at the time of its discovery, the largest confirmed structure in the observable universe. The response from cosmologists was carefully calibrated. The Sloan Great Wall was large, but it could be argued to fall within the outer range of what the standard model permitted. Some researchers pointed out that it sat very close to the theoretical upper limit for structure size in a universe governed by the cosmological principle. The scale above, which homogeneity was supposed to take over and smooth out any further organization of matter. If the Sloan Great Wall was at that limit, it was a borderline case rather than a clear violation. The model remained intact, though it was breathing harder at this end of its range. For about 18 years, the Sloan Great Wall held its title as the largest known structure. During this time, cosmologists continued their surveys, improving instruments and extending the depth and breadth of galactic mapping. The anomaly stood at the edge of the model's predictions, watched carefully but not treated as a crisis. Then, in 2021, a doctoral student at the University of Central Lancashire changed the picture in a way that was impossible to dismiss as a borderline case. Alexia Lopez was analyzing data from the Sloan Digital Sky Survey, specifically looking at distant quasars, galaxies powered by supermassive black holes at their centers and bright enough to be detected billions of light-years away. She found a clustering in the quasar positions that formed a sweeping arc across a large region of sky. As she analyzed it more carefully, the structure's properties became harder to attribute to statistical noise or selection effect. The giant arc, as it came to be called, stretches 3.3 billion light-years from end to end. It sits roughly 9.2 billion light-years from Earth. At the announcement, Lopez said what the data made difficult to avoid, saying, "If the giant arc is a real, coherent structure, the standard cosmological model may be flawed." 3.3 billion light-years is more than twice the Sloan Great Wall and nearly 3 times the theoretical maximum for structure size. The optimistic interpretation of the Sloan Great Wall that the model was holding at its limits was no longer available. The giant arc was not at the limit. It was well beyond it, in territory where the standard model said there should be nothing to find. The announcement of the giant arc raised the obvious skeptical questions that any anomalous structure discovery must face. Was the apparent arc a real, coherent gravitational structure, or was it a projection effect, a coincidental alignment of galaxies and quasars at slightly different distances that appeared to form a pattern when viewed from a specific angle? Was it a statistical fluctuation in galaxy density, a region where the distribution of matter happened to be somewhat elevated without being organized by any physical mechanism? Was the analysis affected by selection biases in the quasar catalog that might artificially produce clustering in certain regions of the survey? Lopez's team addressed each of these concerns carefully in the published analysis. The giant arc appears consistently across multiple traces. The arc appears consistently in the quasars that revealed it initially, and also in the distribution of galaxies and gas clouds in the same region and at the same distance. Projection effects tend to dissolve when you check them against multiple independent tracers at similar distances. The arc does not dissolve. The statistical significance of the structure, after corrections for known survey biases, remains well above the threshold for a discovery claim. The curvature of the arc is consistent across different analysis methods. The probability of the pattern arising by chance from a distribution consistent with the standard model is very small. 3 years later, the same team found something that reinforced the case even further. In early 2024, Lopez and colleagues announced the Big Ring, a near-perfect ring of galaxies with a circumference of roughly 3.9 billion light-years and a radius of about 1.3 billion light-years. The Big Ring sits at essentially the same cosmic distance as the giant arc, roughly 9 billion light-years away, separated from it by about 3 billion light-years in the plane of the sky. Two structures, each independently larger than the standard model permits, found in the same cosmic epoch at the same cosmic distance by the same team using the same survey data. The probability of finding two such structures in proximity by chance, even without accounting for the fact that each one individually has a low probability of existing, is smaller still. The standard model does contain a preferred scale of clustering imprinted on matter by pressure waves in the early universe, called baryon acoustic oscillations. The Big Ring's diameter roughly matches the baryon acoustic oscillation scale, which has led some researchers to explore whether this mechanism might explain it. But the giant arc does not match the baryon acoustic oscillation scale in the same way, and the proximity of the two structures is not predicted by this mechanism. They remain unexplained. Two anomalous structures sharing a cosmic address, and together they form part of a pattern that is becoming increasingly difficult to attribute to chance or incomplete analysis. Step back from individual structures and view the full landscape of what cosmological surveys have revealed about large-scale structure over the past 3 decades. The picture that emerges is one of escalating anomaly. Each new generation of surveys, each new instrument with greater sensitivity and wider coverage, has found structures at or beyond the limits of what the standard model predicts. The Sloan Great Wall in 2003, the Hercules Corona Borealis Great Wall in 2013, the Giant Arc in 2021, the Big Ring in 2024. What emerges is a consistent pattern across 20 years of increasingly precise observation, in which every large-scale survey finds something the standard model struggles to accommodate. There is a way to read this pattern optimistically. Perhaps the surveys are simply sampling rare fluctuations. Even in a universe that is broadly homogeneous, large fluctuations are statistically possible, just unlikely. Perhaps we have been lucky, or unlucky depending on perspective, in our survey directions, consistently pointing telescopes toward the rare regions of the sky where the matter distribution is most extreme. The standard model is not falsified by finding a few anomalous structures if those structures are consistent with the tail of the model's statistical distribution. But the optimistic reading gets harder to maintain with each new anomaly. The Hercules Corona Borealis Great Wall is not at the tail of the standard model's distribution. It is 8 to 10 times larger than the maximum the model produces in any simulation. The giant arc is 3 times the model's maximum. The Big Ring exceeds it similarly. These are not tail events in a normal distribution. They are events at values the distribution does not reach. The model does not predict them as rare. It predicts them as impossible. At some point in any scientific debate, the accumulation of anomalies that the model cannot explain at any level of improbability stops being a collection of surprises and becomes evidence that the model's premises are wrong. The cosmological principle, the foundational premise that the universe is homogeneous at large scales, is what the impossible structures are violating. They are not just anomalies within the framework. They are evidence that the framework itself is built on an approximation that breaks down at the very largest scales we can map. Something is organizing matter on scales far beyond what gravity alone, operating from the smooth initial conditions of the Big Bang, can build in the available time. What that something is remains the central unanswered question of modern cosmology. Cosmic inflation is one of the most successful and least directly tested ideas in all of physics. It proposes that in the universe's first tiny fraction of a second, so brief that describing the duration requires a decimal point followed by more than 30 zeros, the universe underwent a period of explosive exponential expansion. In this time, the region that would become the entire observable universe expanded from something smaller than a proton to roughly the size of a marble. The expansion factor was at least 10 to the 26th power. This sounds like science fiction. It is mainstream physics. The motivation for proposing inflation is strong. Without it, two deep puzzles in the cosmic microwave background have no satisfying answer. The first is the horizon problem. Regions of the sky so far apart that they could never have exchanged information at the speed of light, since the Big Bang nonetheless have the same temperature to 1 part in 100,000. In a universe without inflation, these regions were never in causal contact, so their synchronization has no explanation. Inflation solves this by proposing that the entire observable universe expanded from a tiny region that was in thermal equilibrium before inflation stretched it apart. The uniform temperature is a relic of that pre-inflationary contact. The second puzzle is the flatness problem. The universe's spatial geometry is extraordinarily close to perfectly flat, which requires an extreme fine-tuning of the initial density of the Big Bang, unless some process smoothed it out. Inflation smooths it automatically. Any initial curvature is diluted to unmeasurable flatness by the enormous expansion, just as inflating a wrinkled balloon gradually smooths its surface. Inflation also predicts the spectrum of density fluctuations in the cosmic microwave background, and the prediction matches the observed spectrum with impressive precision. As a general concept, inflation is strongly supported. The difficulty is that inflation makes additional predictions that depend on the specific physics of the inflaton field, the hypothetical quantum field whose energy drove the expansion. Different models of inflation make subtly different predictions about the spectrum of density fluctuations and the statistical properties of the large-scale distribution of matter. Some inflaton models predict features, specific scales of enhanced clustering or particular statistical signatures that would produce structures exceeding the predictions of the simplest standard model. If the impossible structures we are finding are real, they may be encoded messages about the inflaton field's specific properties, evidence for a form of inflation that left a richer imprint on the distribution of matter than the simplest models allow. The universe may not be breaking physics so much as revealing which specific version of physics produced it. There is a harder possibility than non-standard inflation, one that lives at the boundary between cosmology and metaphysics, but that serious physicists take seriously. The universe's large-scale anomalies may reflect boundary conditions imposed from outside the universe itself. In eternal inflation, our universe is one bubble nucleating in a vast inflationary background. The distribution of matter inside a bubble universe is determined not only by the physics operating after its Big Bang, but by the conditions at the bubble's boundary, where its physics meets the inflationary medium that surrounds it. If another bubble universe came close enough to ours to influence its formation, or if our bubble nucleated in a region of the inflationary background that was not perfectly uniform due to the effects of nearby nucleations, those boundary conditions would show up as large-scale anisotropies and structures inside our cosmos. The cold spot, the impossibly large structures, the subtle statistical anomalies in the distribution of galaxy orientations that some researchers have reported, could all be reflections of a geometry outside our universe that we are inheriting without being able to see its source directly. We would be reading shadows on the walls of our cosmic cave, inferring the shape of something outside the cave from the patterns its presence casts on the inside. We cannot step outside the cave. The observable universe is, by definition, all we can observe. but the patterns the outside world leaves on the inside might be distinguishable from purely internal physics if we are clever enough about what to look for. This is not yet a confirmed or even a well-constrained hypothesis. The multiverse is not directly observable, and no measurement has definitively established that any specific anomaly is caused by external influence rather than internal physics we do not yet understand. But it is a coherent scientific proposal grounded in established inflationary theory that addresses multiple anomalies simultaneously and makes predictions that future observations could test or falsify. It represents the most radical possible answer to the question of what the impossible structures are telling us. They are telling us the universe has neighbors, and those neighbors have left their mark. Whatever the explanation, the impossible structures are not going to disappear from the data. They are not measurement errors. They are not artifacts of incomplete analysis. They are features of the universe that the standard model cannot account for, confirmed by independent methods, growing more numerous with each new survey, and pointing consistently at the same conclusion. At the very largest scales, the cosmos is stranger than our best model allows. The next question is whether the strangeness extends to the way we measure the universe's most fundamental property. The Hubble constant is the number that describes how fast the universe is currently expanding. More precisely, it is the proportionality factor relating a galaxy's distance from us to its apparent recession velocity due to the expansion of space. In the 1920s, Edwin Hubble and his collaborators showed that distant galaxies are receding from us, and that the farther they are, the faster they recede. The Hubble constant quantifies this relationship. Measuring its value precisely has been one of the central ambitions of cosmology for nearly a century. The measurement is fundamental. It tells us how old the universe is, how large it is, and how fast it is growing. Two fundamentally different methods now exist for measuring the Hubble constant, and they give different answers. The first method works through the cosmic microwave background. By analyzing the detailed pattern of temperature variations in the background radiation and fitting it to the standard cosmological model, researchers infer the universe's expansion rate at the time of decoupling, then evolve it forward using the model's equations. This method, applied to the Planck satellite's precise measurements of the background, yields a Hubble constant of about 67.4 kilometers per second per unit of cosmic distance. The second method builds a chain of distance measurements in the nearby universe. Parallax measurements of nearby stars calibrate the brightness of Cepheid variable stars. Cepheids calibrate the distance to nearby galaxies. Those galaxies calibrate Type Ia supernovae, and the supernovae extend the measurement to billions of light years. This distance ladder method gives about 73 kilometers per second per the same unit. The disagreement is 8 to 9%. In everyday life, this margin would be negligible. In physics, where two independent and precise measurements of the same quantity must agree if the underlying model is correct, it is a crisis. Both measurements have been checked, rechecked, extended, and refined by multiple independent groups. Both have improved in precision over time. The tension has grown more statistically significant as more data has accumulated, not less. Measurement errors shrink with more data. The Hubble tension is growing. It is almost certainly real. Something in the model is wrong. Either the universe's expansion history is not what the standard model predicts between the era of the cosmic microwave background and today, or there is new physics operating in some epoch of the universe's history that the model does not include. The proposed solutions are many, and none are fully satisfying. Early dark energy, additional relativistic species in the early universe, modified gravity on cosmological scales, interactions between dark matter and dark energy. Each solves the Hubble tension while creating difficulties elsewhere. None have been confirmed. The tension stands, year after year, a gap that grows more significant with more data, pointing at a flaw in our model whose nature has not yet been identified. The Hubble tension is not the only place where the universe's expansion fails to behave as expected. In 2024, the Dark Energy Spectroscopic Instrument released results from one of the most ambitious surveys of cosmic structure ever attempted. This instrument, mounted on the 4-meter Mayall telescope at Kitt Peak in Arizona, is designed to measure the positions and velocities of tens of millions of galaxies across billions of light-years, constructing the most detailed three-dimensional map of the universe's expansion history ever attempted. By tracking how the distribution of galaxies has changed over cosmic time, it provides a direct measurement of how dark energy has behaved across the universe's history. The standard model assumes dark energy is a cosmological constant, a fixed energy density of empty space that does not change over time. The lambda in lambda CDM literally represents this constant. Under this assumption, dark energy has always had the same strength per unit volume of space, and the only reason its influence on the universe's expansion has grown over time is that the universe has expanded while matter has diluted, making dark energy increasingly dominant by comparison. The cosmological constant is the simplest possible form of dark energy, requiring no additional physics beyond Einstein's general relativity with a particular value of lambda. The DESI results hinted, with a statistical significance that was suggestive but not conclusive, that dark energy may be varying over time. The data showed a preference for a dark energy equation of state that changes as the universe ages, consistent with dark energy being somewhat stronger in the past and somewhat weaker today than a cosmological constant would predict. The hint was not strong enough to definitively rule out the cosmological constant, but it was strong enough to make the constant the less preferred option among the models tested. If confirmed by additional data from DESI and from other surveys, dynamic dark energy would have profound implications. A dark energy that changes over time is not described by the cosmological constant. It requires a new field, a new form of energy with its own dynamics and evolution. This field, often called quintessence, would change the expansion history of the universe, altering the predictions for structure formation at various epochs. It could help explain the Hubble tension by changing the expansion rate in ways that bring the two methods of measuring it into better agreement. It could alter the timeline for the universe's fate, changing when and whether phenomena like the Big Rip become possible. And it would definitively mark the end of lambda CDM as the final word in cosmology, requiring its replacement with a framework that goes beyond a constant dark energy. The lambda in lambda CDM would need to be replaced by something more complex, more dynamic, and currently unknown. The DESI survey's methodology is worth understanding in more detail because it represents the most direct probe of dark energy's behavior over cosmic time. The survey uses spectroscopy to measure the precise redshift of tens of millions of galaxies, which tells us both their distance and how fast the universe was expanding when their light was emitted. By mapping how the distribution of galaxies has changed at different epochs, the survey reconstructs the expansion history directly from the galaxies rather than inferring it from models. This is a fundamentally different approach from the cosmic microwave background method, which relies on model fitting to early universe physics, and from the distance ladder method, which chains together multiple distance calibrations in the nearby universe. What the first year of DESI data showed was a preference for dark energy models, where the equation of state has evolved over time. The preferred models had dark energy stronger in the past, when the universe was younger and denser, and weaker today, rather than perfectly constant as the cosmological constant requires. The statistical preference was at roughly 2 to 3 sigma, suggestive but not definitive. It could still be a statistical fluctuation. More data from subsequent DESI observing seasons will determine whether the preference strengthens toward the 5 sigma threshold required for a discovery claim, or fades back toward consistency with the cosmological constant. The cosmological community is watching these results closely because the implications of confirmed dynamic dark energy would require a revision of the theoretical framework used to interpret every other cosmological observation. If lambda is not constant, every result that assumed it was needs to be revisited. Dark energy's most intimate connection to the large-scale structure of the universe is through what it does to the voids. As the universe's expansion accelerates, the gravitational bonds holding matter together at the edges of superclusters are increasingly overcome. Matter at the periphery of structures, material that is only weakly gravitationally bound, gets carried away by the expansion faster than gravity can pull it back. Simultaneously, the voids that dot the cosmic web continue to grow. The underdense regions that formed when matter flowed outward toward the denser filaments and walls are now expanding themselves, pushed outward by the accelerating universe. The Boötes void is not the same size it was 5 billion years ago. It is larger. In 5 billion more years, it will be larger still. This process, played out across the entire cosmic web, is gradually stretching the web thinner. The filaments that today connect clusters of galaxies across hundreds of millions of light-years are stretching and thinning as the clusters they connect are pulled apart by the expansion. In billions of years, the web's finest threads will snap, disconnecting the clusters they linked. Superclusters will dissolve as their outer galaxies drift over the cosmological horizon. The cosmic web, which built everything we know from quantum noise over 13 billion years, is being dismantled by the same dark energy that held it back during the universe's matter-dominated era. For the Milky Way and the local group, the immediate practical consequence of dark energy is isolation. Currently, the local group is gravitationally bound and will not be torn apart by the expansion. The Milky Way and Andromeda are on a collision course that will produce a merger in roughly 4.5 billion years. That merged galaxy, Milkomeda, will remain gravitationally bound to the other members of the local group. But the other galaxies visible in our sky today, the millions of galaxies in the Virgo cluster and beyond, are already receding. In about 150 billion years, the expansion of the universe will have carried all galaxies beyond our local group, over the cosmological horizon and out of sight forever. The night sky of that era would contain only the stars of Milkomeda and the faint light of our nearest local group companions. Everything beyond would be gone, carried over a horizon from which no light returns. A civilization living then would look at the cosmos and see only their galaxy. They would have no evidence of the billions of other galaxies that once populated the observable universe. They would have no way of knowing that the universe had a large-scale structure, that the cosmic web had once filled the sky, that the Hercules Corona Borealis Great Wall had once spanned 10 billion light-years somewhere beyond their horizon. The information would be gone, unreachable, beyond causality. The universe will hide its own history from the creatures that might eventually be capable of reading it. The Big Rip is the most extreme endpoint of a universe governed by dark energy that grows stronger over time. In the standard lambda CDM model, dark energy is a cosmological constant, and its influence grows only because the universe expands while matter dilutes. Dark energy itself remains constant per unit volume. Under this assumption, the universe's expansion accelerates forever, but the acceleration rate does not grow without bound. The ultimate fate is an ever more isolated cosmos, with galaxies drifting apart into cold, dark solitude, but with the matter within galaxies remaining bound by gravity indefinitely. The Milky Way will exist as an island in an empty universe for as long as its stars burn. The Big Rip changes this picture. It becomes possible if dark energy is not a constant but a dynamic field with an equation of state parameter that falls below -1. In this case, the energy density of dark energy increases as the universe expands, rather than remaining constant. As the universe gets larger, dark energy grows stronger. The expansion rate not only continues but accelerates without limit. At some point in the future, the acceleration becomes strong enough to overcome the gravitational binding of galaxy clusters, then the binding of individual galaxies, then solar systems, then planetary surfaces, then solid material, then molecules, then atoms themselves. The timeline of the Big Rip depends on the exact behavior of the dark energy field. Current constraints on the dark energy equation of state, including the hints from the DESI survey, allow for phantom energy scenarios in which the Big Rip occurs within a few billion to a few tens of billions of years. In those scenarios, the destruction begins with the largest structures first. Superclusters dissolve, then clusters, then galaxies are stripped of their outermost material. In the final moments before the Big Rip, the expansion of space on subatomic scales would tear apart atomic nuclei, dissociating the protons and neutrons that make up ordinary matter. Everything the universe built would be unmade. The Hercules Corona Borealis Great Wall, 10 billion light-years of structure that formed in defiance of our best models, would be among the first casualties. The dark energy that currently accelerates the universe's expansion at the cosmological scale would eventually reach the scale of the Great Wall's filaments and push them apart faster than gravity could hold them. Then it would reach individual galaxies within the structure, then individual solar systems, then worlds that might harbor life. The impossible structure would be disassembled by the same invisible force whose nature we don't understand and whose future behavior we cannot confidently predict. We do not know if the Big Rip will happen. We do not know the future of dark energy. We do not know the fate of the cosmic web. The universe keeps its secrets in the very domains where the answers matter most. The anomalies we have been exploring, the impossible structures, the cold spot, the Hubble tension, the dynamic dark energy hints do not exist in isolation from each other. They form a pattern. They are different measurements pointing at the same underlying reality. And that reality appears to be one in which the universe at its largest scales does not follow the rules we built the standard model to describe. The natural question is whether these anomalies share a common cause, or whether they are independent problems that happen to all challenge the standard model simultaneously. There are reasons to suspect a common cause. The large-scale structures that are too large for the standard model formed through a process of gravitational amplification of initial density fluctuations. If those initial fluctuations were stronger than the standard model predicts, the structures would be larger. What could make the initial fluctuations stronger? A non-standard inflationary model with enhanced power at specific scales. Dark energy that was stronger in the early universe than it is today. Dark matter with properties that allowed more rapid clustering. Any of these changes to the standard model's assumptions would affect structure formation across all scales and all epochs. They would produce larger structures today and more massive galaxies in the early universe. Exactly what the James Webb Space Telescope is finding. The Hubble tension fits into this picture as well. If the early universe had more energy in some form that the standard model does not include, whether dark energy, dark matter, or something else entirely, the expansion rate inferred from the cosmic microwave background would be lower than the true expansion rate, bringing it into better agreement with the local measurements. Some proposed solutions to the Hubble tension, particularly early dark energy models, also predict enhanced structure formation in the early universe. They would not only address the expansion rate discrepancy, but also help explain why the James Webb Space Telescope finds galaxies that are too massive for their age. The pattern of anomalies thus converges on a region of physics that involves conditions in the very early universe and the nature of the forces, particularly dark energy and dark matter, that dominate its evolution. Whatever is missing from the standard model may have been present and influential during the universe's first billion years, then faded or changed, leaving its imprint in the structures we observe today. The Hercules Corona Borealis Great Wall, built when the universe was less than 4 billion years old, in a time when whatever new physics was at work was still active, may be the most dramatic evidence that something beyond the standard model was shaping the cosmos in its earliest and most formative epochs. It is an artifact of a universe running on rules we haven't fully learned yet. The observable universe has a boundary. It is not a wall or an edge. It is a horizon, a limit of visibility imposed by the finite age of the universe and the finite speed of light. Light from objects more than about 46 billion light-years away has not had time to reach us in the 13.8 billion years since the Big Bang. Those objects exist. They are part of the same universe, but their light has not arrived yet. And in the case of objects that are receding faster than light due to the expansion of space, their light may never arrive. The observable universe is a sphere centered on the Milky Way, not because we are special, but because every observer in the cosmos has their own observable sphere, defined by their own cosmic horizon. The Hercules Corona Borealis Great Wall sits near the edge of our observable sphere. At 10 billion light-years away, it is visible to us only because we can see light that has been traveling for 10 billion years. The light we receive from it shows the Great Wall as it was 10 billion years ago, when the universe was less than 4 billion years old. We do not know what it looks like today. We cannot receive that information. The present state of the Hercules Corona Borealis Great Wall is permanently hidden from us by the finite speed of light. Beyond the Great Wall, beyond our observable horizon, the universe continues. By how much, we cannot say with certainty. Measurements of the cosmic microwave background constrain the universe's curvature to be very close to flat, which implies a universe that is either exactly flat and therefore infinite, or so enormous that its curvature is unmeasurably small within our observable sphere. The latter interpretation, based on inflationary models, suggests the true universe could be at least 250 times larger than the observable sphere. In models of eternal inflation, the universe could be essentially infinite. Within that unobservable vastness, the cosmic web presumably continues. Filaments and voids, walls and clusters, all built by the same physics or modified physics that produced what we can see. There may be structures out there that dwarf even the Hercules Corona Borealis Great Wall, built by the same anomalous processes that produced the Great Wall and the giant arc and the Big Ring within our observable sphere. We will never map them. We will never know whether they exist. The universe beyond our horizon is a permanent unknown, a vast territory whose contents are inaccessible, not due to technological limitations we might eventually overcome, but due to the fundamental geometry of space and time. The largest structure in existence may not be visible from anywhere. It may exist in the unobservable reaches of an infinite cosmos, assembling itself from quantum noise and dark matter scaffolding, following rules we have not learned and may never learn. The Big Ring's geometry is particularly striking when examined closely. A ring of galaxies spanning nearly 4 billion light-years in circumference, with a diameter close to the baryon acoustic oscillation scale, would require an explanation in terms of known physics if it is a coherent structure. Baryon acoustic oscillations are pressure waves that propagated through the early universe in the first few 100,000 years after the Big Bang, when the cosmos was a hot plasma of matter and radiation. These waves left a characteristic scale imprinted on the distribution of matter, a preferred separation between galaxy pairs, about 500 million light-years. This scale shows up as a subtle excess in galaxy clustering statistics and is used as a standard ruler to measure the universe's expansion history. The Big Ring's size roughly matches the diameter expected from baryon acoustic oscillations viewed as a ring. One possibility is that the Big Ring is a section of a baryon acoustic oscillation shell, the edge of a spherical pressure wave that has expanded since the early universe, captured in 2 dimensions by the survey that found it. If so, it would represent a detection of baryon acoustic oscillations in a new geometric form, which would be scientifically interesting, but not a violation of the standard model. The challenge is that the giant arc, found at the same distance, does not fit into the same baryon acoustic oscillation framework in an obvious way. 2 structures near each other, one potentially explainable by baryon acoustic oscillations and one not, is a harder puzzle than either one alone. The proximity of the 2 structures, sitting at the same cosmic epoch in the same patch of sky, demands an explanation that accounts for both of them. No proposed explanation has yet done so to the community's satisfaction. The detection of the warm-hot intergalactic medium's filaments, in 2020 was accomplished through a technique called stacking, combining thousands of X-ray images of regions between known galaxy clusters, averaging them to reduce noise, and looking for the faint signal that any individual observation could not detect. The approach is elegant precisely because no single image shows the filament signal clearly enough to be recognized as real. Only the collective signal, assembled from thousands of independent observations that each contribute a fragment of evidence, produces a detection. The warm, hot gas in a single filament, stretched across hundreds of millions of light years, is too diffuse and too faint for any individual pointing to catch. But the universe, consistent in its physics, puts the same kind of gas in the same general temperature range in filaments throughout the cosmos. Stack them all together, and the signal emerges from the noise. It was always there. We simply needed enough patience and enough observations to see it. The universe's hidden half was waiting in plain sight for 70 years until the instruments and methods reached the threshold required to reveal it. This is a lesson the anomalies of today should reinforce. The universe contains more than our instruments have confirmed, and the gap between what exists and what we have detected has historically closed, not through the universe becoming simpler, but through our tools becoming more capable. The cosmic web is not static. Every filament, every node, every cluster is in motion. Matter flows along the threads of dark matter toward the densest concentrations, pulled by gravity in a slow drift that has been running since the first structures formed. Galaxies travel along these invisible highways, converging on massive attractors at speeds that accumulate to millions of miles per hour when measured against the background of the universe's oldest light. Our own galaxy participates fully in this flow. The Milky Way is currently moving at over 1 million miles per hour toward a gravitational attractor in the direction of the constellation Hydra. Every galaxy in our local region of the cosmic web is making the same journey, pulled along the local threads of the web toward a concentration of mass that dominated nearby cosmology for most of the 20th century before anyone managed to actually see it. The attraction was obvious in the data long before its source was visible. Surveys of galaxy motions in the 1970s and 80s showed systematic flow, thousands of galaxies in our cosmic neighborhood all streaming in the same direction, toward a point in the sky that astronomers could not examine directly. The reason was mundane and frustrating. The source lay directly behind the plane of the Milky Way. The dense band of gas and dust that marks our own galaxy's equatorial disk is nearly opaque at visible wavelengths, creating what astronomers call the zone of avoidance, a strip of sky from which optical data is essentially unusable. Whatever was pulling galaxies from that direction was invisible behind the Milky Way's own material. For decades, cosmologists could measure the flow but not identify the source. They named it the Great Attractor. Radio surveys that could penetrate the zone of avoidance began revealing the source in the 1980s. X-ray observations mapped it more completely in the 90s. What they found was a supercluster of galaxies in the direction of the constellations Hydra and Centaurus. The Norma cluster and its associated galaxies, a concentration of mass equivalent to roughly a quadrillion times the mass of our star. The Great Attractor is massive enough to exert measurable gravitational influence over a volume hundreds of millions of light-years across. It is enormous by any standard, and it is itself being pulled. Beyond the Great Attractor, the gravitational flow continues toward a still larger concentration, roughly 650 million light-years away. The Shapley supercluster, one of the most massive objects in the observable universe, a gathering of dozens of galaxy clusters whose combined mass dwarfs the Great Attractor as the Great Attractor dwarfs an individual galaxy. The entire local flow field, our galaxy, the local group, the Great Attractor, and millions of other galaxies, is streaming toward Shapley. We are nested inside nested flows at every scale, falling through a structure within a structure within a structure, each level pulling toward the next, all the way up to the largest threads of the cosmic web. In 2014, a team of astronomers used the pattern of these gravitational flows to define our cosmic home in a new way. Instead of drawing the boundary of a supercluster based on the physical positions of galaxies, they drew it based on the flow field itself, the region within which all galaxy motions converge toward a common attractor rather than diverging away from it. Applying this definition to detailed measurements of galaxy velocities across the local universe, they found a supercluster 520 million light-years across, containing the equivalent mass of 100 million billion suns. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea had existed for billions of years before it was named. The Milky Way had been flowing within it since before our star ignited from a molecular cloud. Every galaxy in its volume had been part of its gravitational community for cosmic ages. We had simply not recognized the structure because we had been using the wrong definition. Draw the boundary by flow rather than proximity, and an enormous organized system becomes visible that was invisible under the old criteria. This is a recurring pattern in the study of large-scale structure. The universe contains vast organized systems that we live inside without knowing it. Systems that only reveal themselves when we change what we are measuring or how we are defining our terms. The universe is not shy about its structures. We have simply been learning what questions to ask. The Milky Way sits in the outer regions of Laniakea, not near its center. We are in the suburbs of an immeasurable heaven, one modest spiral galaxy among hundreds of thousands, in a structure we couldn't identify until we had mapped the motions of those hundreds of thousands of neighbors and traced where all the flows ultimately led. Our cosmic address, complete and accurate, is the Milky Way, local group, outer Laniakea supercluster, part of the larger Pisces-Cetus supercluster complex, within a cosmic web that contains the Hercules Corona Borealis Great Wall, 10 billion light-years in the direction of an impossibility we are still working to understand. Laniakea is one of roughly 10 million superclusters in the observable universe. It is not a particularly large supercluster. The Shapley supercluster, toward which Laniakea flows, is larger. The Perseus-Pisces supercluster is comparable. The Sloan Great Wall encompasses many superclusters. The Hercules Corona Borealis Great Wall dwarfs all of them by a factor of 20. We are small in a cosmos of enormous, organized things, nested inside nested structures at every scale, and the scale keeps going up further than our models say it should. But the architecture of Laniakea and the superclusters around it is not permanent. Dark energy is working steadily to dissolve it. Roughly 5 billion years ago, as the universe expanded and matter diluted, dark energy began to dominate the universe's expansion dynamics. Before that transition, gravity was winning across all scales. The cosmic web was actively growing. Filaments were thickening as matter flowed into them. Clusters were merging and building mass. Superclusters were consolidating. After the transition, dark energy began to carry the advantage. The expansion started overcoming gravity at the largest scales, carrying the outermost galaxies of superclusters away faster than the supercluster's gravity could draw them back. Laniakea is already in the process of dissolving at its edges. Galaxies in the outer regions of the supercluster, bound only weakly to its gravitational center, are being carried away by the expansion. In the long-term future, these galaxies will drift over the cosmological horizon and become permanently inaccessible. The core of Laniakea, including the great attractor and the dense clusters near it, will remain gravitationally bound for much longer. But the supercluster as a whole, as a coherent system defined by its inward flow, is already losing its periphery to dark energy. What was built over billions of years is beginning to be unmade. The Milky Way's own future within this picture has a specific timeline. In roughly 4.5 billion years, Andromeda and the Milky Way will collide and merge, producing a large elliptical galaxy that some astronomers call Milkomeda. This merger will not be like cars crashing. the stars within both galaxies are so widely spaced that almost none of them will directly collide. Instead, the two galactic structures will interpenetrate and swing around each other for hundreds of millions of years before settling into a combined system, their gas clouds colliding and triggering bursts of star formation, their supermassive black holes eventually pairing and merging in an event that will release gravitational waves detectable across the local universe. Milkomeda will be the final product of the Milky Way's participation in the gravitational ballet of Laniakea. After the merger, Milkomeda and the other remaining members of the local group will drift together through an increasingly empty cosmos as dark energy carries the rest of the universe away. In roughly 150 billion years, everything beyond the local group will have receded over the cosmological horizon, invisible and unreachable. The universe available to observation will consist of a single merged galaxy surrounded by darkness. The cosmic web, the filaments, the superclusters, the walls including the Hercules Corona Borealis Great Wall will be beyond the horizon, inaccessible and unmappable to any civilization that might exist at that remote epoch. The process by which Laniakea dissolves at its edges has a technical name. The cosmic expansion is carrying its outer galaxies beyond the turnaround radius. The distance at which a galaxy's inward gravitational velocity equals the outward velocity imparted by the expansion of space. Inside the turnaround radius, gravity wins, and galaxies eventually fall inward. Outside it, expansion wins, and galaxies recede forever. As dark energy drives the expansion to accelerate, the turnaround radius shrinks over time. Structures that are gravitationally bound today will find their turnaround radius contracting inward, releasing their outermost members to the expansion. Laniakea is large enough and loosely enough bound at its edges that this process is already underway. The same calculation applies to the Great Wall structures. The Hercules Corona Borealis Great Wall, whatever physical mechanism produced it, is not a gravitationally bound structure in the way a galaxy or a galaxy cluster is bound. Its constituent galaxies are not all in bound mutual orbit. The Great Wall is a large-scale overdensity, a region where the average density of galaxies is higher than the cosmic mean, but not a structure held together by the mutual gravity of its parts the way a cluster is. This means the Great Wall is not immune to the expanding universe. Its galaxies will drift apart over cosmic time, the overdensity diluting as expansion carries members away from each other. The Great Wall, that the Hungarian astronomers detected through gamma-ray burst statistics, is the Great Wall as it was 10 billion years ago. Its current state, 10 billion light-years away and inaccessible to direct observation due to light travel time, is presumably more spread out than the structure we infer from the historical data. The impossible thing that formed is already in the process of being erased. The Big Rip is the most extreme of the universe's potential futures. The scenario in which dark energy does not merely accelerate the expansion, but grows stronger without limit, tearing apart structure at every scale in a final, total unmaking. In the standard cosmological model with a fixed cosmological constant, the Big Rip does not happen. Dark energy is constant per unit volume, so as the universe expands, dark energy's influence grows only because matter dilutes while dark energy does not. The expansion accelerates, but the acceleration rate itself approaches a constant, and the universe asymptotically approaches an exponentially expanding de Sitter space. Galaxies drift apart, clusters eventually dissolve, but gravity holds together the smaller structures indefinitely. The Big Rip requires dark energy to violate this pattern. It requires the dark energy equation of state to be less than -1, placing it in the phantom energy regime. In this regime, the energy density of dark energy increases as the universe expands. More expansion means more dark energy per unit volume, which drives more expansion, which creates more dark energy. The feedback loop has no break. The expansion rate grows without bound, and eventually, It grows fast enough to overcome the gravitational binding of structures at progressively smaller scales. The timeline in a Big Rip scenario works backward from the moment of maximum expansion, which occurs at a finite future time. Roughly 2 to 3 billion years before the Big Rip, galaxy clusters begin to dissolve as the expansion overcomes their gravitational binding. Hundreds of millions of years before the end, galaxies are torn apart. Months before, solar systems. Minutes before, planets. Seconds before, solid objects. Fractions of a second before the final moment, atoms are stripped of their electrons. In the very last instance, atomic nuclei are ripped apart by the expansion of space on subnuclear scales. Protons and neutrons, bound together by the strong nuclear force, are separated as space expands faster than the strong force can reach across. The universe ends not in a heat death of cold darkness, but in a final violent act of disassembly, dismantling every structure that gravity and chemistry and the strong force ever built. The Hercules Corona Borealis Great Wall, 10 billion light-years of structure that formed when the universe was less than 4 billion years old, would be among the first casualties of the Big Rip. An enormous structure torn apart by an enormous force, billions of years before the final moment. The dark energy that makes the Big Rip possible is the same dark energy whose hints of dynamism appeared in the DESI survey data, the same dark energy whose nature we do not understand, the same 68% of the universe that defeats every attempt to explain it from first principles. We do not know if the Big Rip will happen. We do not know the future of dark energy. The cosmos holds its most important secrets in the things it will not let us directly examine. Go back to the beginning. The universe, at 380,000 years old, is a hot plasma of hydrogen and helium atoms, freshly formed as the temperature finally dropped low enough for electrons to bind to nuclei. The fog has just cleared. The cosmic microwave background, the snapshot of this moment, has just been released to travel forever through the expanding cosmos. The distribution of matter is almost perfectly smooth, varying only by 1 part in 100,000. The cosmic web is not yet visible. The voids are not yet empty. The filaments are not yet lit. Everything that will eventually become the Hercules Corona Borealis Great Wall is a nearly invisible pattern of slightly varying density in a universe that looks, to any observer, almost completely uniform. What happens next is gravity. Over the following millions of years, the slightly overdense regions begin attracting surrounding matter. The process is slow, almost imperceptible on any human timescale, but it is relentless. The first structures to form are the smallest, tiny clumps of dark matter and hydrogen gas, perhaps 1,000,000 times the mass of our star, cooling and collapsing in the depths of the Dark Ages, the era between the clearing of the cosmic fog and the ignition of the first stars. Inside these first clumps, the gas compresses and heats. Eventually, in the denser clumps, the conditions for nuclear fusion are met. The first stars ignited somewhere in the universe roughly 200 to 400 million years after the Big Bang. They were nothing like the stars we know, formed from gas that contained only hydrogen, helium, and traces of lithium, with none of the heavier elements that later generations of stellar chemistry would provide. These first stars were enormous. Some were hundreds of times the mass of our star. They burned their fuel at a furious rate, racing through their hydrogen supply in only a few million years, then dying in spectacular supernovae or collapsing directly into black holes. Before they died, they blazed. Their ultraviolet radiation carved bubbles of ionized gas in the surrounding neutral hydrogen, beginning the process called reionization that would eventually make the entire universe transparent to ultraviolet light again. Their supernova explosions scattered the first heavy elements, carbon, oxygen, nitrogen, silicon, iron, into the surrounding gas. Those heavy elements were the seeds of chemistry. They drifted through the early universe and found their way into the next generation of stars and the molecular clouds from which those stars formed. Stars of the second generation formed from enriched gas, their chemistry richer, their lives longer, their planetary systems more complex. Over billions of cycles of stellar birth and death, the heavy element content of the universe built up through progressive generations of stellar nucleosynthesis. The atoms in rocky planets, in organic molecules, in human bodies, were forged in the cores of stars that lived and died long before our star existed. The cosmic web, building these stellar generations in its filaments and clusters, is the forge of everything complex in the universe. The James Webb Space Telescope was designed to see the first galaxies, to look back to cosmic dawn, when the universe was only a few 100 million years old, and observe the earliest structures in the process of formation. The universe at that age should look like a construction site. Small proto-galaxies, irregular clumps of gas and infant stars, merging and building slowly toward the larger, more organized galaxies that would emerge over billions of years. The models of galaxy formation, built from lambda CDM structure formation and refined over decades, made specific predictions. Early galaxies should be small, low in stellar mass, irregular in shape, and chemically primitive, containing mostly hydrogen and helium, with little of the heavy elements produced by later stellar generations. The James Webb Space Telescope found something different. In its first year of operation, it returned images and spectra of galaxies at redshifts corresponding to an era when the universe was less than 1 billion years old, and many of them were far more massive, far more organized, and far more chemically enriched than the models predicted. Galaxies with stellar masses tens of billions of times that of our star, showing disk-like morphologies suggesting stable, organized rotation, with spectra indicating significant abundances of heavy elements requiring multiple generations of star formation to produce. All of this at a time when, according to the standard model, the universe should barely have had time to assemble its first generations of stars. The phrase universe breaking appeared in several popular science articles about the James Webb Space Telescope's early results applied to these unexpectedly massive early galaxies. This was an overstatement in the strict sense. The universe clearly continues to exist, and the standard model is not about to be discarded wholesale. But the early galaxy findings do represent a genuine challenge to the model's predictions for early structure formation. The universe was building things faster than theory allowed. Early galaxies were more advanced than models predicted. The construction site was further along than the timeline suggested. This is not an isolated anomaly. The impossible timeline of the Hercules Corona Borealis Great Wall, too large for the time available, belongs to the same category of problem as the two massive, too organized early galaxies of the James Webb Space Telescope era. The common thread is that structure formation in the universe happened faster than the standard model predicts. Something accelerated the construction, whether it was the properties of dark matter, the behavior of dark energy in the early universe, the details of inflation, or something else entirely. The acceleration is evident in the data at multiple scales and epochs. The universe in its youth was in a hurry to become what it is, and our model was not told what the hurry was about. The accumulation of anomalies from every instrument and every scale forces a question that cosmologists are now asking seriously. Is something missing from the standard model of physics at a fundamental level? The list of candidates is long, and the experiments to test them are running. Modified gravity theories propose that general relativity, Einstein's description of gravity, breaks down on cosmological scales and must be replaced by a modified version that changes the behavior of gravitational attraction at low accelerations or large distances. Some of these theories, like Mond and its relativistic extensions, can reproduce certain observations without dark matter, though they struggle with others. Interacting dark energy and dark matter models propose that these two invisible components of the universe are not independent. Instead, they exchange energy or momentum in ways that affect the expansion, history, and structure formation. Such interactions would change the Hubble constant inferred from the cosmic microwave background, potentially resolving the Hubble tension. They would alter the timeline of structure formation, potentially explaining why some structures are too large. The challenge is that different observations constrain these interactions in different ways, and no single model of interaction fits all the data simultaneously. Dynamic dark energy, given new urgency by the DESI survey hints, is among the most actively studied extensions. If dark energy is a field, quintessence, that evolves over time, its past behavior could have been different from its present behavior. Early dark energy models add a component of dark energy that was active in the first million years of the universe's history, influencing the expansion at early epochs in a way that would shift the Hubble constant inferred from the cosmic microwave background upward toward the locally measured value. Some of these models also predict enhanced early structure formation, helping to explain the James Webb Space Telescope's two massive early galaxies. The appeal of early dark energy is that it might solve multiple anomalies simultaneously. New relativistic species, additional light particles in the early universe that behave like radiation, have similar effects on the expansion rate and might explain the Hubble tension. Primordial magnetic fields, if they existed in the early universe, could have influenced structure formation on large scales and potentially contributed to the anomalously large structures. Non-standard inflation models with specific features in the inflaton potential could have enhanced clustering at particular scales, directly seeding the large structures we observe. The landscape of possible extensions to the standard model is rich. The experiments to test them are increasingly precise, and the convergence on an answer, while not yet achieved, is a realistic goal for the coming decade of cosmological surveys. The pattern in all the anomalies we have examined shares a character that is worth making explicit. Each anomaly, the impossibly large structures, the Hubble tension, the cold spot, the two massive early galaxies, the hints of dynamic dark energy, points in the same direction. At the very largest scales and in the earliest epochs, the universe does not quite behave the way the standard model predicts. The standard model works beautifully at intermediate scales and in well-tested regimes. Galaxy formation, the cosmic microwave background, the distribution of matter up to about 1 billion light-years, the abundance of light elements, all match the predictions to high precision, but pushed to the extremes, to the very largest structures and the very earliest galaxies, and the model begins to fray. This is a recognizable pattern in the history of physics. Every successful physical theory eventually reveals the boundary of its validity, and that boundary is always marked by anomalies. The anomalies do not mean the theory is wrong within its domain. They mean the theory is a special case of something more general, valid within a particular range of conditions and breaking down outside it. Newtonian mechanics breaks down at high velocities and strong gravitational fields, but works perfectly in everyday conditions. The cosmological constant fits the data within most tested ranges, but may be only an approximation to a dynamic dark energy field. The cosmological principle holds approximately at intermediate scales, but may break down at the largest scales, where the impossible structures sit. What makes the current moment in cosmology particularly exciting is that the anomalies are converging. The Hubble tension, the large-scale structures, the early galaxy problem, the dynamic dark energy hints, they are all pointing at the same region of parameter space, suggesting modifications to the standard model in the early universe and in the nature of dark energy. This convergence is exactly what you expect when a set of anomalies shares a common cause. The more they point together, the more confident you can be that there is a real physical effect underlying them, rather than a collection of statistical coincidences. The standard model of cosmology is nearing the boundary of its validity. On the other side of that boundary is a deeper understanding of the universe, one we are only beginning to glimpse. The convergence of anomalies in cosmology today has a historical precedent that is worth examining. In the early 20th century, classical physics was enormously successful. It explained mechanics, electricity, magnetism, and optics with extraordinary precision. But there were a few anomalies. The photoelectric effect did not behave as classical electromagnetic theory predicted. The spectrum of blackbody radiation did not match classical calculations. The orbits of electrons around atomic nuclei were classically unstable. Each of these anomalies was specific, confirmed, and resistant to explanation within the classical framework. Each pointed at the same region, the behavior of energy at very small scales. The resolution, quantum mechanics, was not a patch on classical physics but a completely new framework that revealed classical mechanics as the large-scale limit of something deeper. The cosmological anomalies today are pointing at a specific region, the behavior of the universe at very large scales and in its earliest epochs, the impossible structures, the Hubble tension, the dynamic dark energy, the early galaxy problem. Each one is confirmed, specific, and resistant to explanation within the standard model. Together, they point at something about the early universe and the nature of dark energy that the standard model does not include. The resolution, when it comes, may be a patch, a modification of inflation, a dynamic dark energy field, an adjustment to the dark matter model, or it may be something more profound, a revision of the cosmological framework at a level comparable to quantum mechanics' revision of classical physics. We do not know which it will be. We do not know whether the new framework will require entirely new concepts or merely refinements of existing ones. We do not know whether the answer is decades away or imminent. What we do know is that the anomalies are real, the standard model is insufficient at its extremes, and the universe will eventually yield its secrets to observation and analysis. The impossible structures are the first paragraph of a new chapter in cosmology, and we are only now learning to read the language it is written in. Consider, for a moment, what we actually know directly about the universe versus what we infer, assume, or calculate from models. Of the universe's total mass energy content, we have direct evidence through particles detected in experiments or observed through their electromagnetic radiation for about 5%. The ordinary matter that makes up stars, planets, gas, and humans is all we can directly measure. The other 95% is inferred. Dark matter, inferred through gravitational effects, never directly detected. Dark energy, inferred because the universe is accelerating, with no direct detection of the responsible entity and no confirmed quantum description. We are mapping the largest structures in existence using instruments sensitive to only 5% of what constitutes those structures. We are measuring the universe's expansion rate using stars and galaxies made of 5% of the universe's content and attributing the dynamics to dark energy we cannot see. We are simulating the formation of the cosmic web using a model of dark matter that has never been confirmed by any particle physics experiment. The standard model of cosmology is built on inferred foundations, and when the structures built on those foundations turn out not to match the predictions, it is worth remembering how much of the foundation is inference. This is not a criticism of cosmology. The inferences are well-founded, supported by multiple independent lines of evidence, tested repeatedly against diverse observations. The existence of dark matter is as well established as anything in modern astronomy, even without direct particle detection. The existence of dark energy is beyond reasonable doubt given the supernova data, the cosmic microwave background, and the large-scale structure statistics. These inferences are solid, but their solidity comes from fitting models to observations, and if the models have incorrect assumptions, even good inferences can lead in the wrong direction. The cosmological principle is an assumption. It is a good assumption, well motivated, and approximately correct at most scales. But it is an assumption, not an observed fact. The impossible structures are observational evidence that the assumption has limits. They are not just anomalies within the model. They are evidence that the model's most fundamental premise needs qualification. The universe does not treat our assumptions as obligations. It behaves according to its own rules, and those rules include physics we have not yet discovered. The anomalies are the universe's way of telling us where to look for the missing physics. The story of the Hercules Corona Borealis Great Wall and the impossible structures embedded in the cosmic web is ultimately a story about the limits of knowledge and the method by which those limits are identified and pushed back. Every major advance in cosmology has followed this pattern. A precise measurement, a confirmed anomaly, a theoretical crisis, a resolution that expanded the framework. The discovery of the universe's expansion led to the Big Bang theory. The discovery of the cosmic microwave background confirmed the Big Bang and led to precision cosmology. The discovery of the accelerating expansion led to dark energy and lambda CDM. Each anomaly, in retrospect, opened a door into a larger room. The impossible structures are the anomalies of our era. They have been confirmed by multiple independent methods. They have survived statistical challenges and criticism. They are not going away, and they are joined by the Hubble tension, the dynamic dark energy hints, the early universe galaxy puzzle, the unresolved nature of dark matter. The pile of what the standard model cannot explain is growing taller with each survey. The door is visible. What lies behind it is not yet clear. What we can say with confidence is that the resolution, when it comes, will change how we understand the universe at its most fundamental level. If the cosmological principle fails at large scales, the models of cosmic expansion need revision. If dark energy is dynamic, the fate of the universe needs recalculation. If structure forms faster than predicted, something in the physics of the early universe is different from what we assumed. Any of these changes, singly or in combination, would propagate through the entire framework of cosmology, changing how we read the cosmic microwave background, how we interpret galaxy surveys, how we calculate the universe's age and fate. We are at a moment in the history of cosmology comparable to the moments before the discovery of dark energy, before the discovery of the cosmic microwave background, before the discovery that galaxies exist beyond the Milky Way. A moment when the anomalies are confirmed and the new framework is not yet in hand. A moment of productive confusion, where the old answers are clearly insufficient and the new answers have not quite arrived. The Hercules Corona Borealis Great Wall, 10 billion light-years of impossible structure, is the largest anomaly in this collection, and the most dramatic sign that the universe runs on rules we are only beginning to understand. Zoom out one final time from where we stand. Leave the Milky Way, traveling outward through Laniakea, past the Great Attractor, past the Shapley Supercluster, past the Sloan Great Wall, past the Giant Arc and the Big Ring, continuing outward until the Hercules Corona Borealis Great Wall comes into view at 10 billion light-years, a vast concentration marking the largest known organized structure in the observable universe. Continue a little further until the entire web fills the perspective. Filaments and nodes and voids stretching in every direction, built from dark matter and gas, and the gravity of billions of years, seeded by quantum fluctuations from an era before time, as we normally understand it, began. This is where we live, in a universe that built something impossible and placed us inside a pale, ordinary corner of it. In a universe whose skeleton is invisible and whose dominant force is unexplained. In a universe that is accelerating toward a future of increasing isolation and whose most fundamental properties, the expansion rate, the nature of dark energy, the behavior of structure at the largest scales, are in active dispute among the most capable scientists alive. We live in a universe that is telling us, through every anomaly and tension and unexplained structure, that the model we built to understand it is not finished. It is very good, and it is not finished. The Hercules Corona Borealis Great Wall did something impossible. It formed 10 billion years ago, when the universe was young and the physics that built it was active, and the processes that produced it were running on rules we have not confirmed and may not have guessed. It has been there ever since, waiting for a civilization capable of detecting the gamma-ray bursts of its dying stars across billions of light-years, capable of running the statistical analysis to recognize what the clustering meant, capable of grasping the physical implications of a structure this large in a universe this old. That civilization is us, assembled from the heavy elements forged in ancient stellar furnaces, organized by the same chemistry that runs in every living thing. Gazing outward through instruments of extraordinary precision at a universe whose nature is still being negotiated between our models and its reality, we are brief, we are small, we are standing at the edge of what is known, looking at something 10 billion light-years wide and asking how it is possible. That question is everything. It is the most honest thing about what we are. Arrangements of matter complex enough to wonder about the arrangement of everything else. Living in a cosmos that rewards wonder with more questions, deeper questions, questions that require larger frameworks and more precise instruments, and a willingness to find that what we knew was insufficient. The universe built something impossible, and the least we can do is figure out how. We have not finished yet. We are only beginning. And the beginning of that work is the most exciting place a curious mind can be.